Today, we're going to do something a little different. We're going to deconstruct an entire real-world engineering job using just one single document, a job description. We're going to build a complete picture of a tech role, the CAE engineer, right from the ground up. And it all starts with a simple question. It kind of sounds like a riddle, right? Car manufacturers, they have to make sure their cars are safe, and that means crashing them. But think about it. Building and then destroying dozens and dozens of prototypes, that's incredibly expensive, and it's super slow. So how do they do it efficiently? The answer, as you might have guessed, is in the digital world. They build a perfect virtual twin of the car on a computer, and then they crash it thousands of times in a simulation. The technology that makes all of this possible is called computer-aided engineering, or CAE for short. And the people who are in charge of running these digital crash tests, well, they're a special kind of engineer. So in this first part, let's explore exactly who they are and what they really do. A CAE engineer is, in a way, like a digital fortune teller for physical things. They use this unbelievably powerful software to see into the future, to see how a car part will bend or how it might break or buckle under stress, all before a single piece of actual metal is ever stamped. Okay, now let's get specific. We're basing this whole explainer on a real job posting from a company called Greaves Technologies. So what is the core mission for their CAE engineer? You know, it all boils down to two things, safety and performance. Their entire job is focused on one critical task, building the most accurate digital model they possibly can. Why? So that when the team runs a virtual test, the results are actually trustworthy. The quality of their work has a direct line to the safety of the final car. It's a huge responsibility. So this big mission really breaks down into three key areas. Crash analysis, that's pretty self-explanatory. It's a direct collision simulation. Durability, well, that's all about testing how a part holds up over time. It's like simulating 100,000 miles of bumpy roads. And then there's structural analysis, which tests the fundamental strength and stiffness of the car's individual pieces. So how do they actually do all this stuff? I mean, you can't just draw a car in Microsoft Paint and click a crash button. It takes a highly specialized digital toolkit to get the job done. What's so great about this slide is how it separates the tools from the ideas. On the left, you've got the actual software names like ANSA and LS-DYNA. You also see NASTRAN there, which is another heavy hitter often used for structural analysis, testing how things react to stress or vibrations. But on the right, you have the fundamental engineering principles they're used for, like meshing or defining connections. A great engineer has to master both sides, the software and the theory behind it. Let's start with ANSA. Think of this as the prep stage. An engineer gets a raw 3D design, and it might have tiny little flaws in it. They use ANSA to clean it all up, and then they cover it in this intricate digital net, which is called a mesh. This mesh is what allows the physics simulation to actually work its magic. Okay, so once the model is all prepped and meshed perfectly in ANSA, it gets handed over to LS-DYNA. And this is the main event. LS-DYNA is the beast, the powerful engine that takes that pristine model, applies all the laws of physics, and runs the actual virtual crash test. It then spits out just a massive amount of data about what happened. So we have the tools, and we have the mission. Now let's connect all the dots and look at the daily workflow. This is really how an engineer turns that list of responsibilities into an actual step-by-step process. And this slide right here lays out their day-to-day perfectly. It's a really logical flow. They start with a raw design file and they clean it up. Then they build that all-important mesh. Step 3 is absolutely crucial. This is where they tell the software how every single part is connected. Every bolt, every weld, everything. Only then can they finally run the simulation and, at the very end, check the results to make sure they're accurate. And they aren't just simulating the entire car all at once. The job description specifically calls out sheet metal and plastic components. So they're focused on things like door panels, bumpers, fenders, the parts that are on the front lines during an impact. All right, so we've seen what they do and how they do it. But what does it actually take to become a CAE engineer? The job description gives us the exact profile of the kind of candidate they're looking for. This experience requirement is actually really telling, 1 to 4 years. So this isn't a senior level lead architect role, but it's also not for someone fresh out of college with zero practical experience. They're looking for someone who already knows their way around the software we just talked about. And here are the nuts and bolts. The role is a CAE engineer, it's located in Chennai, and they need someone who can start pretty quickly, within 45 days. This tells us it's probably for an active, ongoing project that needs help right now. Let's bring this all together. When you strip away all the software names and the technical jargon, this is what's left. A CAE engineer is a digital architect of safety. Their entire job is to find the fatal flaw in a design while it's still in the virtual world, so that it never, ever has a chance to cause harm in the real world.
So, I'll just leave you with this thought. That 5-star safety rating you see on a new car, it's not just a sticker. It represents thousands of hours of work by an engineer meticulously building, testing, and digitally crashing that car over and over and over again, all to make sure you and your family are safe out there on the road.